Hello everybody, Mr. Hasty here again. We're going to continue our discussion of section 8.1, which is on indeterminate forms. So today we're going to tackle two different indeterminate forms. The first one is 0 times infinity. So let's have a quick discussion about how we can apply L'Hopital's rule to 0 times infinity. Well, we learned when we talked about limits that something that is infinite can be modeled with limits as 1 over 0. So this expression is equivalent to 0 times 1 over 0, which is 0 over 0. And thus we can apply L'Hopital's rule. So the basic strategy we're going to have here is to convert one of our terms into a fractional form to make our statement that we will then apply L'Hopital's rule to. So we're going to look at two examples, but the first one we're going to show you in two different ways. We're going to show you in a very straightforward way, and then we're going to show you a trick that is often used when doing these types of problems. So I believe this is example 7 in the section. I could be wrong about that. But let's say that we have the limit as h goes towards, x goes towards infinity of x times sine of 1 over x. Now, quickly, let's kind of think about what this means. Clearly, if we plug in infinity, x would be infinity, but 1 over infinity is 0, and the sine of 0 is 0. So this would be infinity times 0. So how are we going to apply this here? Well, we have to turn one of our statements into a fraction, and it is easier to turn x, instead of multiplying by x, we're going to divide by the reciprocal. We're going to get the limit as x goes to infinity of sine of 1 over x over 1 over x. So again, multiplying by x is the same as dividing by 1 over x. And the reason why this works is because we would get 0 on the bottom and sine of 0, which is 0 on top. Therefore, we can apply L'Hopital's rule. Now, the derivative of the top is tricky. We need to do a product rule there. Chain rule there. So sine of 1 over x is going to change to cosine 1 over x. Put that in parentheses. Times the derivative of the inside. Remember, 1 over x is x to the negative 1, so the derivative is negative 1 over x squared, or negative 1x to the negative 2. There's two ways to think about it there. And on the bottom, the derivative of 1 over x is going to be, again, negative 1 over x squared. Now, in a lovely fashion, those cancel, and we get the limit as x goes to infinity of cosine of 1 over x. So that would be the cosine of 1 over infinity, which is the cosine of 0, which is 1. First problem done. Now there is a nicer way to do this problem, but it is a little odd. It involves what we call a replacement variable. So if we look back at the original statement, I'm going to do a variable switch. I'm going to make a statement that x is equal to 1 over h. Now you're like, what is h? That has nothing to do with our problem. I'm literally choosing a variable name. You could make it a, b, h, z. It does not matter. So if I want to rewrite this in terms of h, if x is going to infinity, then h would have to be going to 0 to make those equivalent. And I can replace x in my original statement with 1 over h. And I can replace 1 over x, if we think about what that'd be 1 over h, which would be h. So you get sine of h. And this is very, very easy to turn into a fraction that L'Hopital's rule applies to. You just take the fraction and move it onto the denominator. So I get sine h over h. Now this was actually a limit we memorized way back in chapter 2, but let's say that you didn't memorize it. You can still, if you plug in 0, you're going to get 0 over 0, so we apply L'Hopital's rule. And you get cosine h over 1. And if you plug in 0, you get cosine 0, which is 1. Same answer either way. But a lot of textbooks use the second method because it's considered cleaner. However, there's nothing wrong with the top method. It just involves a bit more of a mess with your fraction work. All right, I'm gonna clear this out and we're gonna move on to example 8. All right, so example 8 here, we're gonna look at a limit as x approaches 0 from the right of the natural log of x. Natural log of x times x. So in this case, we usually try to take the thing that is less complicated to make our fraction. So we're doing it from the right here because if you remember what natural log looks like, it looks like this. So as you approach 0 from the right, it goes to negative infinity. But as x approaches 0, it's just 0. So this comes out to be negative infinity times 0. So I'm actually going to choose to put the x on bottom. And I'll do that by remembering that multiplying by something is the same as dividing by the reciprocal. So ln x over 1 over x. And that's our trick for dealing with every one of these. You can either do variable substitutions like I did on the last problem in the second part, or you can do these kind of fraction works. Now, as I check this, the natural log of 0 from the right is negative infinity, and 1 over 0 is going to go to some sort of infinity. So we have an infinity over infinity, we can apply L'Hopital's rule. So, derivative of natural log of x is 1 over x. And the derivative of 1 over x, we talked about last section, is negative 1 over x squared, or last problem. We can simplify this and get one over negative 1 over x. I basically canceled a 1 over x off the bottom by canceling with the top. And dividing by a fraction is the same as multiplying by the reciprocal. So dividing by negative 1 over x is the same as multiplying by negative x. And if we plug 0 in there, we're just going to get 0. Now, in this situation, this problem, no matter if we put any constant out in front of this, is going to work out to be 0. That's not true of every single type of problem. Some types of problems are always going to work out to be a 0 or an infinity, but there's quite a few that could come out in multiple different forms. All right, we're going to move on to the next indeterminate form we're going to cover today, which is infinity minus infinity. So the indeterminate forms of infinity minus infinity happen to be my favorite. Let's fix that grammar right there. So I'm not going to show you a general approach here, but basically it is always going to be a situation where we get common denominators in order to work this out. So a simple example of this would be something along the lines of the limit as x goes to 0 of 1 over x minus 1 over x squared. So if we look at this, 1 over 0 is infinity, and 1 over 0 squared also infinity in terms of limits. So we're simply going to get a common denominator here in the standard approach. So I'm going to get x over x squared minus 1 over x squared. Multiply the left fraction by x over x, combining them. We get x minus 1 over x minus x squared. Now, that will come out to be, if we plug in 0, negative 1 over 0. Now, because if we plug in 0, we don't get 0 over 0, infinity over infinity, we can't apply L'Hopital's rule. So we actually just have to simply apply something from earlier experiences, which is you can do some factoring and cancellation to get limits. So I get x minus 1 on top, and if I factor out an x, I get, let's factor out a negative x. I will get x minus 1 on bottom, canceling those. I will get 1 over negative x. And if we plug in 0 here, we're going to get 1 over 0, and that's going to be an infinity. The question would be, would that be a negative infinity or positive infinity? And the answer is, it depends on kind of the direction. If we really want to be honest here, this limit is not going to exist, because if you graph negative 1 over x, you get this guy, and the left and right are both going to say opposite infinities. So you could say this one does not exist, but it's because you get infinity. When you get infinity, you got to check, is it positive infinity, negative infinity, or it does not exist. All right, let's look at example 10. So we'll do the limit as x goes to 1 of 1 over ln x minus 1 over x minus 1. So briefly here, the ln of 1 is infinity. It's actually negative infinity if you're coming from the, the ln of 1 is 0. 1 over 0 is infinity. And 1 minus 1 is 0. 1 over 0 is infinity. So again, we're going to try to apply a common denominator here. The left side is going to need x minus 1 top and bottom. I'll put that in parentheses on the bottom. And the right side is going to need an ln x top and bottom. Now, again, we're going to have to combine the tops. X minus 1 minus ln x over the quantity x minus 1 times ln x. So here's where we got to check to make sure we can apply L'Hopital's rule. So if I plug 1 into the top, I'm going to get 0 minus 0, because remember, natural log 1 is 0. The bottom, I'm going to get 0 times 0. So again, that's fine. Now that we have 0 over 0, we're going to apply L'Hopital's rule. So derivative of the top, derivative of x is 1, derivative of negative 1 is 0, and derivative of natural log of x is 1 over x. The bottom is going to be a bit more difficult. We have to do a product rule there. So the first thing I'm going to do is the derivative of x minus 1. We're going to call this f and this g. The derivative of f is 1, so I'll just get a natural log of x, because I'll get 1 times natural log of x, plus the x minus 1 times the derivative, which is 1 over x. Now, if we plug 1 in here, we get 0 on top, and we end up getting 0 on bottom. So I'm going to clean up the bottom here a bit. I'm going to get ln x plus, when we distribute the 1 over x, we get 1 minus 1 over x. I just distributed the 1 over x. Now we're going to apply L'Hopital's rule again, because we still have 0 over 0. Hopefully don't run out of space here. And I get negative 1 over x squared, because the 1 is going to 0 out, and the 1 over x is going to become, that should be positive 1 over x squared. That would be the negative in front canceling with the negative in the derivative. I'm going to use the simplified version here. Derivative of natural log of x is 1 over x. 1 with 0, and the derivative of negative 1 over x is positive 1 over x squared. Now, one way you can think about doing this is if you just multiply the top and bottom by x squared, it'll cancel all your fractions except for the big one makes it a lot easier. So limit as x approaches 1. I'm going to multiply by x squared on top and get 1. I'm going to multiply x squared on bottom and I get x plus 1. Now, when I plug 1 into this, I get 1 over 2. And so that's our answer. Next time we'll be going over the exponential indeterminate forms. So, see you tomorrow.